So welcome to the Survivor session. I think everybody that made it here in time today is by definition a hero. Before we jump into the actual speeches, there's two announcements. One is there's no lunch today except for participants of the General Assembly and the people that attend the Extreme Networks workshop in the afternoon. So if you leave right after the plenary sessions, please don't go to the lunches because then there won't be enough food for the people that it is intended for. The other thing that's important is you should drop off the bus passes downtown. At the rector's office where the speaker's reception was, there is a drop-off box. We also try to organize a drop-off box at the hotel where we met for the buses, the Molino Molario. Please do drop off the passes. They're not valid on the line that goes to the airport, so you cannot save any money by keeping it. And the cards are really the most expensive part of the deal with the bus company. And so we had really great support from the public transportations, but they asked us to really return as many cards as possible because obviously they cost money. So, having said that, no, that was not the one I wanted. I'm not sure which one is. This one? Yeah. I should better plug in that mouse. So our first speaker is Javier Jimenez, and he will introduce himself. So.
Okay. So, good morning. I really thought that we were going to be even less people after yesterday's beers. So my name is Javier Jimenez. I work in Telefónica R&D, located in Madrid, basically. I work in the new network technologies department. So our main goal there is to make technological analysis of future-proof or promising network technologies, mainly focus on the core network, core fixed network, and somehow link from the research work that is done within Europe and within different forums, and to make some kind of technological transfer to the business units of Telefónica. So the goal of this speech will be twofold. Somehow, first of all, I would like to introduce the Forward project, which is where this kind of activities has been developed. And secondly, I would like to give you some opinion of how virtualization is seen from an operator's perspective. Okay, both from a business point of view, but also from the technical side. So, IST Forward. Forward is currently running FP7IP project. It's indeed one of the major initiatives within Europe to challenge the future internet. It has been running since January 2008, and it will finish December this year. But we really hope that there will be a second phase. We will see what happens. So the main goal of Forward is to try to make a wide research on the combination of clean slate approaches to address the future internet challenges. So you can see here 4 of the basic principles of Forward. One of them is let 1000 networks bloom. That is, instead of trying to develop a new future-proof unique network architecture where all the services will be built on top of it, why not to think about let different architectures coexist over the current internet? A second tenet would be let networks manage themselves. We are really pushing for self-configuring, self-discovering, and self-managing networks. From an operator perspective, this is one of the key challenges of networks, to reduce really the operational expenditures on them. Third of it, we have the idea of why not to investigate if the transport path, what we have now as, for example, TCP, why not to make it an active unit? An active unit means that maybe it can change during the flow transaction. It can be support mobility, multipath, resilience. It can be somehow something more intelligent than what it is now. And finally, there's also people working on the last principle, which is let networks be information-centric. So you can imagine, rather than routing packets to this IP destination, why not to route to the content? I mean, make some network-centric contents available. Okay, so how does network virtualization fit into this picture? Well, somehow virtualization is seen as one of the key tools to support the 1000 networks Bloom principle. So somehow, if we can use virtualization to deploy parallel internets or parallel internet architectures over the same infrastructure. The goal of Forward with dealing with virtualization is try to achieve a consensus between different actors in this framework, from industry, vendors, operators, to research people. So the goals within Forward project are, first of all, to achieve one common architectural consensus, how the architecture for the generalization of virtualization would work or would look like. Secondly, to develop those technologies that will permit to make virtualization. For example, there's people working with virtualization in routers, people doing virtualization on wireless access and wireless networks. I mean, there are plenty of people making some kind of brainstorming on how to take virtualization to any kind of network. And finally, the third goal will be to demonstrate somehow in small testbeds how this architecture will look like and how one could instantiate virtual networks on demand. This is a picture somehow which summarizes the different key roles that we have identified in the virtualization framework. We'll have infrastructure providers in charge of slicing the resources and reselling them to VNet providers. The VNet providers could be in charge of composing end-to-end VNets, for example, achieving agreements with infrastructure providers located in different countries or in different network segments, for example, and also being able to provide a unique single point of access to the VNet operator, who would be a final client of the VNet. Indeed, this is let's say, we try to split different roles into the really specific functions, but to be honest, many times we will see probably that infrastructure providers and VNet providers will probably be the same kind of entity. So in the real world, things are not so easy. So we could imagine that in the future, if virtual networks widespread, we will have some infrastructure providers out there that really offer slices of their equipment to third parties. But we will also still see legacy operators, which we will still have to interoperate with. And we will probably see vertically integrated operators, that is, operators that virtualize their own infrastructure and somehow cover all the value chain from top to down. Some challenges here are not only the vertical relationships between the different roles, but also the horizontal relationships and agreements between in a peering basis. So now some tips about network virtualization from an operator perspective. So what we understand for network virtualization, we understand that virtualization is a tool to provide or to support the concurrent operation of different networks over the same infrastructure. Okay, how it works, you already know. You slice the resources, you compose the different slices to build up VNets or virtual networks, and then you try to assure the correct and proper isolation between the different virtual networks. And why an operator wants to at least have a look on this kind of technologies? Well, at least we have two reasons for that. One of them is, for sure you know that the future internet, let's say paradigm and so on, thinks that virtualization may be one of the key tools in the future networking. We understand this idea and we want to deep a little bit on it and see what is the real use of virtualization. But secondly, there is an industry-led push for virtualization. For example, we have seen in this conference some presentation from Juniper showing some equipment that already does some kind of virtualization, even in hardware. So why not to put some effort on trying to check what is this virtualization all about? Anyway, I can give you in advance that the benefits and opportunities are still not really clear for an operator. For example, why not to make some brainstorming about possible applications of virtualization? So in the left-hand side, you would see, let's say, the more realistic ones, and in the right, some disruptive approaches. And in the top line, we have uses focusing on, let's say, network excellence and lowering the cost of networks. And on the bottom, we have new revenues, let's say, new services that may arise from virtualization. So first of all, we can think that virtualization may be used to lower the capex of an operator. How? By putting all the services that you have over the same network efficiently. We will talk about this a little bit later. Secondly, there is the use case of really selling your infrastructure to third parties. To be honest, this use case is a little bit unclear yet, but from a technical perspective, it seems that it seems feasible that some infrastructure providers could resell their resources to third parties. For example, we may think about content-oriented networks, for example, renting some kind of network for peer-to-peer or to Google, YouTube, or this kind of third parties, and maybe search for income sharing. And some other more futuristic business models. So why not, instead of reselling your own infrastructure, why not to be more ambitious and try to change the whole value chain? For example, an operator could sell its network to a system provider, so to Alcatel-Lucent or to Ericsson, who knows, and forget about managing your own infrastructure and focusing on the business. And well, this is a really challenging idea, but why not? It could work. Other approach could be, what if, for example, the European Commission forces all the incumbent operators to split into the business and the infrastructure, as it happened, for example, in the UK? Well, in this scenario, for example, virtualization could be a tool for the, let's say, infrastructure provider to lower its costs. And finally, talking about really disruptive future internet services, why not to think about VNets or on-demand VNets, for example, when the South Africa football World Championship, why not to deploy a on-demand virtual network to transport all the television traffic from South Africa to the rest of countries around the world, and then after 2 months or 1 month, just turn the network down and have this kind of opportunity window to have some revenues. Other kind of things we would think about would be to have really this paradigm of the parallel internet architectures running at the same time over the internet, no? Or maybe why not to really sell VNets to end users and to give this as an open API for, like, I don't know, other companies, Google or YouTube, do, to leave people the opportunity to build their own networks on demand, and I don't know, start to selling their own services. We will focus a little bit on the two more, let's say, short-term businesses. one of them would be reselling the network operator infrastructure. I mean, why not to use virtualization as a tool to virtualize your own infrastructure and to slice your resources into your different business units? So for example, you would think that would have been a good idea 10 years ago when we had to deploy the mobile networks, because we had, for that time, or we still have a core network for internet, we have a core network for mobile, we have different networks for IPTV. Every time we develop a new service, we have to usually deploy a new network. If virtualization had been there for a few years, we could have deployed only one network and then slicing it and providing new resources every time a new service arises. In the future internet, we would think maybe about having one internet slice within an operator. Then, for example, one slice focused on media services, providing quality of service and efficient distribution, I don't know, multicast features or this kind of stuff. The good thing about virtualization is that you can have different control planes and different ways of forwarding traffic in the different slices. Why not to have other slice focused on the cloud computing paradigm? No, I'm trying to provide both network and computing resources at the same time. Well, this is the idea. Somehow in the roles here, we will be merging the network service provider and the infrastructure provider, and we would be using virtualization within the network operator. Anyway, virtualization has also some let's say, drawbacks. Somehow is that you lose the statistical multiplexing. I mean, if you slice your network and isolate the different slices, you are losing efficiency somehow, in the sense that if you only have one network, it will be used by all the services simultaneously, and you would make a better use of the resources. So there is somehow some concerns about the number of, let's say, virtual networks that may be running over the same infrastructure. Other thing that we talk about is reselling VNets to third parties. What is this all about? Well, somehow we could think about this service as a next generation VPN, in which we not only provide, let's say, circuits, but also routing capabilities or routers here and there. Well, it's okay. And the benefit for the user will be that maybe they can deploy their own routing protocols or their own topology, or even potentially their own internet architecture, I don't know. But to what extent is this realistic? I mean, apart from maybe in the end runs or in the research area, do real clients for VPN banks, for example, or content distribution networks really want to have, apart from capacity, routing capabilities? I'm not really sure about that. And what is more important, what is the business model here? Because if you ask for the client, they will say, oh, I would like to have this kind of network, dynamic networks, and I manage them, but I want them cheaper than the current connectivity services. But on the other side, the operator will say, no, I have the VNet services already deployed, or the VPN services deployed, so this for me, this is an enhanced services, so it should be more expensive. So we have here some kind of disagreement that I'm not sure if we'll finish in something useful or not. That will depend for sure on the business perspective. So just to end with some things about how to deal really with this in the core networks of the operator. For example, think that we really want to provide this kind of VNet services. And we already have an IP MPLS code. How to deal with that? Well, I could think that we have to deploy virtual nodes and virtual links to have a virtual network. So on one side, we need virtualizable routers. Do we need that all the routers be virtualizable? Maybe not. Maybe we can have the point of presence to connect to the clients, virtualizable, so in the edge of the network. And maybe we can have some dedicated big routers with virtualizable capabilities in the core, but only small farms of them, so that in case one client really wants to have one central router to make some kind of routing decisions, we can provide them in very specific places. And we can still use the rest of the network as, let's say, just for transport the traffic. On the other side, we have the virtual links. How to deal with virtual links? For sure, we already know how to virtualize the links. We have ATM, we have VLANs or Ethernet, let's say tagging, we have MPLS, we have many tools to perform, let's say, multiplexing or virtualization of links. Indeed, for example, one may think that why not to use the current MPLS network to virtualize these links between the different virtual routers. But somehow the VNet purists talk about isolation, that the routers and the links should be isolated from the rest of them. And somehow this is not the approach that operators usually have. Operators really want to exploit statistical multiplexing to have different links from different services sharing the same infrastructure, and then over-provision or have some quality of service tools, but for sure not to have isolation. So this is something that we have to really think about. On the other side, we have scalability. How many VNets we will have? We will have the same VNets as circuits that we have now, or we will have, for example, VNets, and then on top of these VNets, the clients will start to establish circuits and so on, because maybe the number of circuits will exploit exponentially in a square basis. So we have somehow scalability and isolation as the main challenges for link virtualization. For example, what if we wanted to use MPLS and these virtual routers to provide virtualization in the core networks? Maybe MPLS would be good because you know that tagging approach, that you have label tags. For example, you can use the inner label to identify, let's say, the client, the real client that is, or the VNet that is using this circuit, and then the outer label to really switch the packet through the network. This could also solve the scalability issues. I mean, the core routers don't have to really follow all the different, or be aware of the different virtual links that they are transporting. They can just transport link aggregates and leave all the information or all the intelligence of the virtual links at the edge of the network. But how to deal with link isolation, for example, in MPLS? This is not clear at all. And how many links we will have? Does this scale? Doesn't this scale? We don't know. There are different approaches here how to proceed. Somehow we could forget about these technologies and develop a new tagging technique, especially designed for VNets from scratch, solving both scalability and quality of service issues. I'm not sure this is the way to follow. We could also use MPLS as it is right now and forget about isolation and just have the virtualization on the routers and the links use what we have. Or somehow we could think about enhancing available protocols, identifying the needed requirements, and proposing them in the standards. So, some conclusions. From an operator perspective, virtualization has a strong potential of use in the future. I'm sure that we will see virtualization in the networks. Somehow, maybe not in such disruptive business cases as one may think, or maybe one may think for the e-science or research area, but we already have virtualization in the network somehow, and virtual routers are already there, so we will deploy them for sure in the future. Anyway, business cases are still not clear, so we have to think about them and really search for them in order to virtualization to become real. Somehow we are also facing some technical challenges. In case we understand or we identify a business case, how will be the network's use to solve the challenge. And finally, I would like just to say that Forward is focusing and it's aiming at providing solutions to all these, both technical and business challenges. So thank you very much, and time for questions.
Any questions?
Okay.
Transport layer, yes. Is it also possible to use PBB or
Yeah, I mean, sure. Any let's say, multiplexing or transport layer technology can be used and could be adapted for network virtualization. As I focused in MPLS because it's the most widespread technology and it's what we have now. But for sure, we have been evaluating PBBTE or MPLS-TP or even optical networks. And we will probably see some of these networks in the future. So one of the challenges of virtualization is also how to virtualize different technologies, how to virtualize the optical layer, what kind of virtualization we will have and what kind of technologies we will use in the core. Yeah.
Any more questions? Comments?
Okay.
Then. Thanks again.
Thank you very much.
So, welcome to our next speaker. Maybe you say a few words about yourself before you start.
Okay.
Thank you.
Hi, everyone. My name is Juan Antonio Martinez, and I work in the autonomous in the Universitat Autònoma de Barcelona in the network department. In fact, as you see here, we should do this speech myself and Martí Griera, who unfortunately is not here, not due to network problems, but to a bike problem, hopefully solved soon. Okay, my presentation will be on how to design a network core or for business continuity architectures in campus environments. The agenda we will follow is, first of all, let's see what are we talking about the context, or how are the campus networks today, how have they evolved, and what should we expect from them. In addition, what do people ask, especially our CEO, for example, what does he want from our network? When we see this kind of networks, tomorrow's network, we ask for many functionalities, and we can see different approaches to solve the problems that arise. The manufacturer approach, first of all, and then after talking to all these people, what is or which is our vision and our solution. We'll see some considerations when implementing or migrating from traditional campus topologies to new topologies, and after all, some conclusions. Well, which are the current trends in general in business networks, or in any network, but particularly for campus networks? Well, some years ago, we talked about network availability, about the 5 nines model, having the network always 99.9% available. But nowadays, we speak about it, but we speak more about business continuity. We need the service to be always on. In addition, in this crisis environment and so, we are asked to do it for less money, do it cheaper, or, let's see, some efficient investment. And also, and the manufacturers are doing it the green way, or trying to reduce all the emissions and all that stuff. Finally, what do we think about when applying any solution? Well, two classic operational principles that are critical for us. First of all, we think that if you want to success, you should fit to standards, and in addition, try to keep everything simple. If you keep things simple, then it's possible that you succeed. If you try to make complex topologies and so, it's more likely that you have problems. Well, in short, what does our CEO ask or want from us? Well, the question is simple. Could you implement a network that, that easily accommodates distributed services, not being tied to any specific manufacturer, and in addition, in a cost-effective way? That would be the question. Well, let's see. First of all, which is the initial step, or where do we come from? First of all, we have a network that is quite simple. In fact, it has a concentrated routing engine, which is the core of the network, and many buildings connected to this central network. Any of these buildings can be linked either through one fiber or two fibers, but in any case to a same centralized engine. This network is easy to troubleshoot. Let's see, we see that the intelligence of this network is in a single point. We have central routing and switching around, and it's really important for us. I don't know if many of you have 24/7 operation, but in fact, it's not the same to troubleshoot a problem today in 2 hours or do it at 2 in the morning. It's really difficult to have a complex topology and to be at the same time able to troubleshoot easily at night or any time. So for us, it works quite well. It's not really complicated, and we have a highly redundant core that in theory, when we bought it, we said, okay, you will have no problems and service continuity is guaranteed. But in practice, it has not always been so. Due to electrical problems, due to some kind of misconfiguration, the central element also suffers from problems. Fortunately, not too often, but it does. And also, we have a double internet connection with 2 different routers, but in fact, in the same physical location, and also, in fact, with the same provider. Well, being more specific, we have something that many of you, I'm sure, that have in your requirements. So we have a Cisco router as a central intelligent equipment. And we, as I have already said, we link the buildings with either 1 or 2 fibers to the main core. We also have this topology also supports with no problem VLAN distribution for specific activities, and for example, wireless or IP telephony. And the main servers are protected with a firewall blade in this central core. When we go to the building, we have switching, and in fact, we are not tied to any vendor. We have 3Com, Nortel, HP, we have any kind. We try to keep every building in a, what we say, single color, or just one manufacturer, but in fact, it's no problem to mix, for example, 3Com with Nortel or with any other. We distinguish 2 levels, the switching core and also the user outlets. And when we return to the center, we have the internet connections with also 2 Cisco equipments that connect to the central core. We also have transparent firewalling, but everything works in a quite simple way. Well, can we expect something more, or does this topology fit or solve all the needs we have for the future years? Well, in fact, there's one big problem, and if the core of the network fails, everything is, well, it's a total disaster. And it has happened to us. In fact, we have, for example, total shutdown, and we give no services to anyone in the campus. We also have redundant links, but yeah, converging to a single point, so something is missing here. And we have double internet connection, but in the same location. Well, what should we want? We want something that it's easy to operate. That's first of all, that's really important for us. We have 24/7 operation, but we don't have, let's say, top-level engineering at any time during the day. We would like to move from a centralized to a distributed model. We want to be, or to keep doing standard way, and please, no complex solution. We have, as I will say, just in a couple of minutes, you talk to the manufacturers, and they have proprietary solutions that are really impressive in functionality, but you lose the real knowledge of what's happening inside this network. This has a problem for us. We cannot troubleshoot so easy, and in addition, it's more easily, or you can have more human mistakes. Well, with these ideas in mind, we talked to many manufacturers, let's say Cisco, Juniper, any others, and we say, okay, what do you recommend for me to do, or what should I do to mount this new network? Well, some words that arise when you talk to them are BSS, or virtual switching technologies, or making some kind of virtual routing, either with more or less standard solutions, or going to proprietary routing, or proprietary black boxed models. Well, in general, apart from this, they have one little problem for us, and we were talking about 150 to 200,000 euros for the campus core. So, as an additional consideration, you have to spend a lot of money, and you cannot mix or so easily mix manufacturers in the core. In fact, we don't want to mix different, for example, putting together Cisco and Juniper in such specific areas as the core of the network. We have no problem to do it in the buildings or so, but we want to have, let's say, a simple and standard solution. Well, do we have any kind of alternative, or can we do anything different? Well, we think we can. The most simple for us is doing, we thought, okay, we can change, we can distribute the intelligence, but do we need really to have a really intelligent core of the network? Well, we thought, why not we go again for switching? In fact, we had switching in the past, and it has worked quite well. So why not switching again? We have thought about implementing switching in the core and making it reliable through classical models like spanning tree or fast spanning tree or any other well-known protocols. And this makes a distributed core by design. We make a second center with a second core, and we link with simple switching topology. When doing this, we make a distributed routing layer. We can do two separate routers as a central routers with direct connection, either 1 giga or 10 giga, and also with direct connection through two different paths to the internet. This can provide an additional level of redundancy because we can have a total failure of one of our centers, and the whole university, or at least the centers that have double connection, can keep working. And how do you place the services in this model? Well, some of them are really easy to accommodate. For example, you can DNS or DHCP are really easy to move around this central distributed core, and we also have application mechanisms to deal with some others. We also have load balancers and so to distribute among the two different centers. Well, which is then the future picture? We want a simple switching core. Switching is really reliable and we have no much problem with two different cores. One if in the main data center, that is the center we have now, and we have asked for a second space in the campus. I think, well, this is for our campus network, but I think it can be easily portable to other kind of environments. You move to this second place the critical services. For example, in the case we are dealing with, we put the web services, the mail service, and these services that are really, really important for the university. In addition, we distribute the internet access through two different locations. So if one of our locations fails, we always have the other one. For this redundancy, we deal with BGP to our internet provider, that in fact is CESCA. And inside we deal with, or we'll try, because we have not made the whole migration yet, but we try to keep HSRP inside and BGP outside. Well, which is the roadmap to arrive to this kind of topology. This can be done in a quite straightforward way, and we can do it quite fast, but both economic and risk management considerations made us to be or to make a progressive approach. It was easier to go step by step, and also, let's say, our politician people in the university wanted not a huge disruption in the network. So the steps are, first of all, decide which will be the second location. Then once you have this location and you accommodate all the facilities, electrical and so, you have to provide the network equipment for this building. Well, maybe you have, in our case, it's new. You can try to make the test with one building. This building can be a real one, or you can try with, let's say, Phantom. And you accommodate test best services. For us, it was quite easy to try to make some tests with something like a web server that you can try that everything works fine. And finally, begin to distribute the other services. First of all, the network attached services like DNS or DHCP, and then you can begin to segregate buildings. In fact, it's quite easy because we come from a routing model, and all we make is move the router from the central point to the building. So it's you have to change no addressing or so, and it's not really difficult. As I said, although we have made this work for our campus, we think it can accommodate to any other network with minor modifications. Well, anyway, if you decide to make this kind of migration, you have to keep in mind some considerations. First of all, migration from concentrated routing to a distributed is quite simple. In fact, you should have no change in addressing, so that was one of the most important points for us. We made some kind of ordering some years ago, and well, it has quite a lot of work to do. People with static addresses, firewalling with a specific IP addresses allow it, and you have to make a lot of change. Well, now you don't have to. It's evolution, it's no disruption. In fact, the model is one step more, but you don't have to throw all you have. The routing is simply moved. You have it already in the core, but you have to move to the building base. What about redundancy? Well, you have it, and it's not really, it's nothing new. It's classical layer 2 protocols that provide well-proven redundancy. The accommodation of distributed services is critical. We don't think that, or in the case of a university, maybe in other environments that's not so, but in the case of the university, we only move critical services. We don't have enough room to place all the services in this second data center. We just put what's critical for us. That includes both DNS, the DHCP as network services, and also web servers, mail, and some databases and so on. Okay. For network operation, it requires no specific additional complexity. It's dealing with switching protocols in the core. And well, yeah, we introduce maybe BGP in the access to the internet, but it's not so complicated as making virtual routing inside the core network. So for us, we think it's a good solution. And in addition, when making tenders and so to provide equipment, we think that you have real competency. Maybe you finally choose one or one manufacturer, but you have, well, the option to choose. And that's important for us because in some previous tenders, we had the idea that, I won't say any names, but there are manufacturers who know that they have all the options to win the tender, so that's a problem when talking about costs. As a whole, we have a substantial cost reduction in the model we want to implement. Okay, and finally, to sum up, some conclusions. First of all, the market is talking about business continuity architectures and new protocols, new architectures like virtual switching, virtual routing, black boxes that transparently make you everything. We think that this can be achieved with classical protocols, and well, we try to be or to rely on these well-known protocols to do the job. We will believe in standards. We think that one of the biggest or one of the better things we have had in the network environment is a standard, is IP, is anything you want, but try to keep doing it in a standardized way. This will be the best way to make the network run smoothly. Well, if we have these ideas in mind and we combine switching in the core and distributed routing, we can have a reliable framework for service continuity. And finally, for us, well, it was critical, but I think it should be said, if you have no economic constraints and you have no problems about human knowledge, you have high engineering in your environments, well, you can try other solutions. For us, it was really important to keep the cost as low as possible and also not to deal with really, really complex topologies, but you can also have really, really good solutions specific to any manufacturer, and maybe they fit for you. And well, that's it for me. If you have any questions or comments.
Thank you. Hello, Han. I have a comment and two questions for you, very, very short. The first question, the first comment is we use this same model in your institution, and that performed quite good. But the only problem that I think, and that is the first question, is the problem with when you use layer 2 solutions for the convergence in the stability in the network, we have some problems. It's especially for the IP telephony and solutions like applications like that is not so fast. I turn a little bit to the solutions over the layer 3 on the routing, and I don't think you have made some tests with the layer 2 convergence and the speeds of the convergence of the network. And the other is what solution are you thinking about the distribution of the DNS and the DHCP?
Well, regarding the first question, yeah, you're right. In fact, when I passed the model, I said, well, our and future model, because we have, let's say, made it in paper and testing with a test bed building, but we have not developed to all the campuses, or to all the buildings in the campus. So the most important for us is that you can accommodate either layer 2 or you can easily change if you want. The most important point from us was distributing the routing from the core to these remote buildings. Okay. Yeah, it's right. Maybe, well, if you have experience with it, it's important for us to know that you can have problems when dealing, even I suppose, with fast spanning tree or so. Maybe for this kind of services. I suppose for data, it's really not so much.
No,
a
for
problem,
data it's not critical.
but for telephony or okay. In fact, we only have now one building with telephony over IP in our campus. We are planning to do the second one right now. So we just wanted, let's say, the paper to support this scheme with also the telephony. But it's good to know that maybe we can have problems. We really don't have tested this movement, this spanning or fast spanning tree, with telephony running over it. So I cannot not really say it works for us, because that would not be true. Regarding the second question about the placement of, you mean the placement
DNS
of...
and DHCP.
Yeah, we have the central, well, let's say the space between all the buildings is for us a layer 0 network where we place seamlessly in one or another building. And for us, it's the same. We only have a matter of moving in a critical thing. If we even want to have the same IP address in one data center and the other one, well, we had to clean the ARP addresses around, but we could even move the same IP address and from one building to, well, from one core building to another core building, because in fact it's the same logical subnet for us.
And if you distribute, if you distribute the routing, you can use mechanisms like the Anycast, announce in the routing the same IP on the two buildings, and try to do the routing, do the work for you with the
two different
with the same IP. With the same IP.
Okay. In fact, the routing from our network to outside is one of the points. As I said, we had direct IP addresses and with no kind of balancing. But, well, we had a load balancer also for some things, but we had only one path, so there was no need to worry. We are just now moving. Inside the network, we had hot standby redundancy protocol, and we thought, in fact, we thought it was not compatible with BGP outside, but we have found that it's possible to implement BGP to the outside and keeping the HSRP inside. So I think we can deal with it.
Okay, thank you.
Any more questions? Okay, so thank you very much again for sharing your new campus design. Thank you. So, welcome to our last speaker, and again I ask you to briefly introduce yourself and then show us how you do this on a grander level.
Okay, thank you. And thank you to all the people that are here in this last session just before the closing session. Well, I am María Isabel Gandia. I am the leader expert of technology at the communications department of the Supercomputing Center of Catalonia. And this is the agenda of my presentation. First of all, I will introduce the network and the CESCA, the Supercomputing Center of Catalonia. Then I will explain how virtualization has been used to build the new core of the network, and at the end, I will explain a couple of examples of use. CESCA is a public consortium created in 1991 by the local government, 9 Catalan universities and 2 research centers. And the network, Anella Científica, was created in 1993. We get our connection from Rediris, and from Rediris we connect to the research network GIAN2 and to the rest of research networks in the world. And on the commercial side, we use the commercial internet connection of Rediris, but we also have our own internet connection for some institutions that cannot meet the Rediris requirements. We also have the management of the exchange point CADNIX, created in 1991, 10 years ago. And we manage to do BGP with all the institutions that are in CADNIX and with the commercial internet providers. So Anella Científica is a kind of regional research and education network. It's the high-speed communications networks that connect the universities and all the research centers in Catalonia, not only scientific, because the meaning of Anella Científica is scientific ring in English, but this doesn't mean that we only have scientific institutions, because there are also researches in history or languages or things like that, food, for instance. CESCA, as the manager of this network and as a local internet registry, has addresses for the connected institutions. We have a /15 of IPv4 addresses and a /32 of IPv6, and we have our own autonomous system. But we are a local internet registry since 2004. Before 2004, the connected institutions had provider-independent addresses. This is the case of the Autonomous University, of the University of Barcelona, for instance, or addresses from Rediris. So, as the providers of this research network, we have to provide services to everyone, and this means all the universities and research community, and this means that not everybody will have Ethernet, because sometimes we have very small institutions that are just on the top of a mountain or near a river that are studying some kind of fishes. There's only one person there that only needs an ADSL connection, for instance. So we don't have fiber and we don't have Ethernet there, just an ADSL is enough for them. As I said, not everybody is in the Barcelona area, so we have radio links too, because not everybody has fiber. We give services to enterprise researchers, and this means that these people cannot use the Rediris connection to the internet because Rediris doesn't accept enterprise researchers. So we have an alternative connection to the internet, and we have special projects on regular traffic, and this means we have to have special circuits for some special projects and dedicated fibers and quality of service, and of course, both unicast and multicast, and both in IPv4 and IPv6. This is the membership policy that we have. We have 3 types of institutions, type A, B, and C. For A and B institutions, we can use the Rediris connection. For C institutions, this is for technological and scientific parks, and for hospital departments different from research departments, we have our own connection that now is provided by Orange. These are all the institutions we have. If you are curious about one of the acronyms, I can tell you what the meaning is, but it was impossible to put 72 institutions in the same slide. So the colors mean the connection, the bandwidth connection. The universities have 1 gigabit per second, most of them, and medium institutions have fast Ethernet connections, and then there are institutions with 10 megabit per second and small connections with via these ADSLs. Regarding the projects, we have many active institutions that participate in international projects. For instance, PEAK participates in the Large Hadron Collider. They are at tier 1 of the Large Hadron Collider, and they have a connection of 10 gigabit per second for it. The I2CAT Foundation participates in Federica and Phosphorus, as you have seen these days, and they have a 10 gigabit per second connection for these projects, as well as a 1 gigabit per second connection for the regular traffic. The Polytechnical University of Catalonia participates in UQS, MapBet, or other projects, and they have, again, 1 gigabit per second for the regular traffic and 1 gigabit per second for these connections projects. There are also 3 institutions participating in a Spanish project similar to Federica, but that in a Spanish way it's called Pasito, and we have a card of 10 gigabit per second for it, with the participation of the I2CAT Foundation, UPC, and CESCA. And we also do temporal increases of bandwidth for those people that need it. For instance, the Hospital Clínic de Barcelona, the Fundació Clínic per la Recerca Biomèdica, used to have a connection of 10 megabit per second in the past, but they used to have this DVTS video conference for endoscopies, as you could see yesterday in a demonstration they did from Japan. So they participated in the APAN meeting and in the CESNET conference, and they needed to do DVTS, and DVTS needs 30 megabit per second, so we increased the bandwidth no cost for them. And we also have the Liceu, the Opera House of Barcelona, that transmits the non-Opera Oberta course. So this is the evolution of the network. In 1993, we began with an Ethernet technology over DQDB and with a core of 34 megabit per second, and we have done many stages of this network. In 1998, we passed to ATM, as many European research networks, as Redis or as the former 10155. And in 2003, we returned to Ethernet. In 2008, we began the last stage of the network. This meant that we had changes in the core network and changes in the equipment. The changes were in this way. We used to have a central node with separate layer 3 equipment for institutions of type A and B and for institutions of type C. But the level 2 and level 3 equipment was the same for most of them. As there are several layer 2 projects involved, we wanted to separate as much as possible this layer 2 from the layer 3. So we had to prepare the call for tenders in July 2007, and to prepare it, we carried out a survey among our users to just know their needs, know what they were going to need in the future. And we asked about the connection needs, the evaluation of our services and dissemination activities, and the planning of new deployments to know their needs. These were the answers. More or less, they say that they were going to need this in the future. As we can see, the points of access were going to be between 68 and 69 in 2009 today, but today we have 82 points of access, so we have increased the number of points of access more than expected, but the network was capable of accepting this. And the local connections, we're expecting to have only one with 10 gigabit per second. Now we have 2. We expected to have only 5 institutions between 1 and 10 gigabit per second, and we have more than 10. And the aggregated bandwidth was supposed to be less than 20, and we have more than 40. So the requirements of bandwidth are bigger than they were expected, but the network can manage it. The requirements that we saw from this survey were these. We saw that we had to increase the bandwidth. We had to have an asymmetric and flexible model to cover these needs of the people that needs a 10 gigabit per second connection and of these people that need a 2 megabit per second ADSL connection. So the policy had to be adaptable for relevant projects and for regular traffic. And we had to have redundancy in the core nodes, in the accesses, etc. So it was clear that if we wanted this redundancy, we had to evolve towards a distributed network. And we thought the best thing was to have 2 points of presence interconnected and to redund the layer 2 and layer 3 equipment. The connections could be or with our own fiber or fiber from the university, or renting fiber to the operator, or having bandwidth from the operator. So this was the schema of the network in 2006. All the institutions were connected to one node, Campus Nord, or to the operator, and from the operator there were two connections to Campus Nord, and from there to Cadnix or Rediris and the internet connection. And this is the schema we have now. A, B, and C institutions can be connected through any of the two nodes directly, or through the operator, and from the operator to the two nodes simultaneously. And we have a double connection from Campus Nord and from Telven to Cadnix and to the internet and to Rediris. The new core of the network, we begin with the previous topology. We had a Catalyst 6513 for the level 2 and level 3 for AB institutions, and a Cisco 7200 for the level 3 for the C institutions. If we see only the site of Rediris, this level 2 and level 3 equipment was connected to the Nortel that Rediris has in Barcelona, also in our facilities, and from here to the Juniper they have for the level 3 in Barcelona. We spoke BGP between our equipment and the Rediris equipment, and we also had the internet connection from Rediris and from the Orange connection for the C institutions. All this equipment was in the same location. This is in Sesca, Campus Nord. But as the managers of the Internet Exchange, we had another point of access in a hosting location called Telven Housing in another building in Barcelona. So we thought that this was a good point to begin, to have another equipment, another core node in the Telven Housing. To explain the call for tenders we did, this is what we asked for. We could not say we wanted any vendor. We wanted level 2 and level 3 equipment in the two core nodes, in Campus Nord and in Telven. And it had to be modular, scalable, with redundant power supplies, manageable via SNMP, have good performance in regular conditions, support bandwidth reservation, quality of service, MP-less, multicast, IPv6, etc. The virtualization was not a must in our call for tenders. It was an improvement, as we said, as we knew that not all the vendors could offer us virtualization. And we also said that the old equipment, this 6513 on this 7200, could be reduced, improved. Its cards could be replaced. It could be used in any of the nodes for level 2, for level 3. It was up to the offer to say what was going to be the new design. We explained all the characteristics that our equipment had, and then I will go one slide backwards. We said that the equipment we had all these characteristics. In fact, they were the same characteristics that we were asking for. So maybe that was the reason that we had 3 offers, and in the 3 offers, sorry, the equipment was from the same vendor, Cisco. So we chose Cisco, obviously, and we chose the more advantages for us with separate layer 2 and layer 3 equipment in one node in Campus Nord, and the same equipment in the other. Final topology was this. We have these two nodes. I don't know if this works. No. Here we have the 6513 we used to have, but it's changed. The supervisor has changed. And now here we have the layer 2 connections. Here we have a Catalyst 6509 with the level 3 connections for the institutions that go through Rediris. And here we have, well, through Rediris and through the operator. And here we have another Catalyst 6509 for the level 2 and level 3. The connection between the two core nodes is a double, it's a 10 gigabit connections between the level 2 node and the node of Telven, and 2 1 gigabit connections to the level 3 node just for backup. And we have dynamic routing between the two nodes. So we have segmentation of functionalities of level 2 and 3 in Campus Nord. We have 2 different types of supervisor, one for level 2 and one for level 3. And we use virtual routers because it's good for us, it's easy to create, and we can use it for projects, for pre-production, but also for other reasons. Why do we use virtualization? Why is it good for us? Because we have different types of institutions and different types of addresses. So we need at least 3 routers for these 3 types of institutions. With virtualization, with only 1 physical router in each site, we can manage everything. We can also use it for pre-production environment and for special projects. And we can also offer the institutions a virtual router separate for its campus LAN. An institution with many points of access that needs a router can ask us for this router. And this virtualization in the level 3 allowed us also to take an ISP approach more than a campus approach and to control everything on the layer 3 because some parts of the layer 2 network are under the control of the operator of Orange, but the layer 3 is only under control of CESCA. So we prefer to have the control on the layer 3 network because we have all the layer 3 control. And this way, with virtualization, having more nodes in the future would be easier. With only 1 physical box, we can have more physical and more virtual routers. So we have changed from 1 node to 2, from 1 piece of equipment to 3, and from 1 physical router to many virtual routers inside each one. And we have also one big change is that we speak dynamic routing with the institutions. We used to have only dynamic routing with the providers. Now we have dynamic routing with the institutions to let them have this backup in the layer 3, sorry. Imagine this box is one of the nodes, Campus Nord node. Inside it, we have addresses, institutions that have addresses from Redis, from the autonomous system of Redis, institutions that are type A or B but have CESCA's addresses, institutions that are type C with CESCA's addresses, and we also have the exchange point. These 4 routers are exchanging, importing and exporting routes from one to the other in different manners. So, for instance, the 2 routers that have CESCA addresses are importing and exporting routes from the router of CADNIX, but Redis router is not exporting routes from the router of CADNIX. And another change is that with this kind of exchange between routers, people connected to 1 virtual router will see any of the other institutions connected to another router only 1 hop away. We don't see 2 hops. If we are on router C and there's another institution on router A, they only see 1 hop from one to the other. We have exactly the same in Delven, and we are exchanging these routes using MPLS with different tags. We also speak OSPF for the infrastructure addresses and BGP for the rest. So this is the core, as I said, but we also have institutions, and we also have our 2 providers, Redis and Orange. For an institution type A or B with addresses from CESCA, we have virtual LANs in the layer 2. So each institution has 1 VLAN to Campus Nord and 1 VLAN to Delven, and from this virtual router, we have 1 VLAN to Redis in Barcelona and 1 VLAN directly to Redis in Valencia. Valencia is another city in Spain, so we are speaking directly with another layer 3 equipment of the NREN. Just in case there are problems in Barcelona, we can go directly to Valencia. It is exactly the same for these institutions that have addresses from Redis. And it's a little bit different for the institutions type C because they also have 1 VLAN to Campus Nord and 1 VLAN to Delven, but we are not speaking with Redis, we are speaking with 2 different routers of Orange in Barcelona. We also have the peering of the ISPs in CADNIX. These addresses we get from CADNIX are exported to the 2 routers of CESCA addresses, but not to the router of Redis, because Redis is also connected to CADNIX. This is a simple example of the routing we have with Redis. If we see, this is the Campus Nord node, and this is the Delven node. Each institution has these 2 VLANs speaking BGP through them with the 2 core nodes. There's BGP and OSPF between the 2 nodes, and there's BGP with CADNIX here and here. There's BGP with Barcelona, with Redis in Barcelona from the node in Campus Nord, And there's BGP from Telven to Valencia using this layer 2 connection. So we get redundancy between the nodes of Sesca, between CADNIC's nodes also, and with Redis or Orange in the case of the C institutions. What about the management? What changes have we found? Well, it's more complex. We have more equipment, more than before, more dynamic routing. We used to have only dynamic routing with Redis and Orange. Now we have with providers and institutions. We have more interfaces to connect with the operator. We used to have 2, and now we have 20. We have more VLANs because we had only 1 VLAN before with each institution, and now we have at least 2. And there's a new syntax. There's not a separation between the virtual routing and forwarding instances in the routers in these boxes, in Cisco boxes. So every time you have to write a command on the CLI, you have to put the VRF. And there are some false friends because the router will accept the legacy commands. So it will accept a show IP BGP summary, but you won't see anything if you put this command because you have to put show IP BGP and then VPN before that's a routing table, VRF and the name of the VRF summary. If you don't do this, you will see that there are no neighbors, and that's not true. There are also one thing that you cannot do now, it's a ping, a regular ping, because you have to put ping and the name of the VRF from where you are doing this ping. We also have new good friends, that's the aliases, because for these very, very long instances that we have to write, we can put just alias, exec, and then one word that we know and all the sentence we want to write. For instance, we don't do pings now, we do peers, PS, and pars, because in different virtual routers we have different pings. And we also say always use include, but do not abuse of includes, and if you need very long includes or very hard includes, then do a grep with a text file in another machine and not in the configuration directly. During the deployment, we found some problems, because in this kind of boxes, by default, all the interfaces have the same MAC address, and this can lead to problems if you have 2 interfaces or 2 VLANs to the same switch. If, for instance, you have an IPv6 and IPv4 interfaces, it can be possible. Then you will have flaps, and you have loss of packets, and you don't know exactly why, since you have to change manually the MAC address. We also found a problem is that for IPv4 multicast, it is not supported in the VRFs, so we had to keep it in the physical on one VRF. And IPv6 was not recommended in the virtual routing and forwarding instances, so it was an experimental command, and we kept IPv6 in the physical machine rather than in the VRFs. Other wish list is that tagging of the routes is per VRF and not per prefix. It is supported by Cisco, but we didn't find much documentation. That it would be desirable to enter the configuration of each virtual router instead of having all the configuration in a plain text file, and you cannot have separate environment for separate virtual routers, and that the name of the VRF cannot be changed. So after the deployment, we had 2 bugs that we had to solve, and the workaround was don't do show run, don't look at your configuration. It was nearly impossible. If you want to manage your router, you need to do show runs. And the maximum number of routes, that is approximately 1 million. If the routing tables of the internet increase considerably, we may face a problem. We may have to change something because we cannot have so many full routings if we have hundreds of thousands of routes. And a couple of examples. This is the case study of the University of, the Autonomous University of Barcelona, the University of Juan Antonio that has presented before. They have Bellaterra as the main site, but they also have many points of access geographically separate. So for them, we have 1 VLAN from each point of access to the 2 nodes, with the possibility of having BGP or not, or static routes, as they prefer, with each point of access. We also have one VLAN for the multicast because they prefer it separate. They also have separate virtual LANs from Bellaterra to each point of access. And they also have used a special VLAN for projects like the Electronic Learning Singing project in the Performing Arts project. They also have the Large Hadron Collider institution in Bellaterra with this WDM 10 gigabit per second connection. And this is more or less all the mesh of virtual LANs of the Autónoma. And another case study of the use of the virtual routers, in this case, if this, IRTA is a food research center. They do research in food. They only need very small connections because they are only 1 or 2 researchers in each center. And they have a main point of access in Barcelona. So each point of access has a connection to one virtual router specifically created for them, and then from this connection to the Barcelona center, they have their internet connection through one of the virtual routers. And this leads to the end of my presentation. Thank you very much for your attention, and if you have any questions, please.
So thanks for the presentation, the overview of your work. Any questions, comments?
Jürgen Weiß from University of Mainz. Which kind of routing protocol do you use towards your customers?
BGP, too.
Thanks.
We use private AES with them, and we change the AES when we announce the routing table to the providers.
Any more questions, comments? Okay, so thank you again.
Thank you.
Thank you to all the speakers.